Thank you very much for kind introduction, and also I thank the organizers for very kind invitation to give a talk at this workshop. So I'm sorry that I cannot visit in person, but I'm very happy to present a talk by Zoom. So this is a joint work with Dean Xue in Shinshu University, and also Masato Hoshino in Osaka University, and Sunda Sethuraman in Arizona. This is the plan of the talk, and first I introduce a quasilinear stochastic PDE, actually singular stochastic PDE, which is derived from the zero-range process in random environment by a hydrodynamic limit. Then actually we consider its integrated form. This is a particle density equation. Then the integrated form is something like a KPZ equation, correspond to KPZ level. This corresponds to the stochastic Vargas level. Then we present in a general form for the stochastic PD in general form, local solvability and continuity in the enhanced noise. And also for the SPD obtained from the hydrodynamic limit, we show the global solvability and also convergence to the stationary solutions. If I have time, I give some proof of these sections theorem. So let me start with the derivation of the quasilinear stochastic PD from zero-range process in random environment. This was done by Landim and Sethuraman and also the other co-authors. And they considered zero-range process in the 1D discrete torus as usual with the size n with the jump rate g in the some macroscopically smeared random environment, which I call the Guzai epsilon x. X is the macroscopic variables. And they derived this stochastic PD because coming from the environment. So environment means, Anyway, environment determines the direction of the jump, okay? So anyway, they derived this equation, if you know hydrodynamic limit, then it's very common to see that this first term. And then this gives a direction, therefore it's a gradient term, so a drift term. Again, this form. Phi is, as usual, the average of the jump rate G under the generalized Poisson product measure new law. Anyway, we will use only the smoothness of phi, and phi prime is uniformly positive and bounded. We will only use this property of phi. So the problem is to study the limit as epsilon to 0 for this stochastic PD. Because they started with the smeared, but the macroscopically smeared random environment. But it is desirable to start with the IID random environment. But if we start the IID random environment, we naturally get the noise here, the spatial Gaussian white noise Guzai. Which is mean 0 and Gaussian covariance is given by a delta function. And this is only spatial, not a space-time white noise, but just a spatial white noise. So we want to show that as epsilon tends to 0 for this equation, we expect this term converges to the spatial Gaussian white noise. So that I want to discuss. So then we consider actually the integrated form. So V is the derivative of U, and for the equation for U, we consider this equation. Then if we take A to be the phi prime, then we can recover the equation we had in the first page. So V is the gradient of the U. So U is the integrated form because if you put V with the gradient of U, so we consider just 1D. Therefore, this is a spatial derivative. Then you take a derivative of this equation in space. Then you have this form, for example, from here. Then if A is a phi prime, then you have this. Then this becomes a gradient at the derivative of phi B. Therefore, you can recover the equation which I wrote in the first page, for instance, from here. Then the second term also, if G is equal to phi, I think then we can recover the original equation. So we consider slightly general equation for the integrated form. Then, okay, so then in the d-dimensional case, spatial Gaussian white noise has a regularity like minus d over 2 and minus slightly bad. Therefore, roughly saying for this equation, due to the Laplacian here, by the Schauder estimate, we expect the solution belongs to this space because the noise is in this space, noise is in this space. Therefore, maybe a solution, if we can solve, then the solution should live in this space. However, this gradient, so the derivative should have a meaning. This should have a meaning. That means this U should be, say, the C1. Therefore, 2 minus d over 2 should be bigger than 1. This restrict our studied only to 1D. If d is greater than 2 or equal to 2, we cannot discuss this problem. If we take Gaussian white noise in space variable. Then I make a comment that the equation for V has a conservation law because you have a derivative here, Laplacian, and also derivative here. So this equation, second equation, has a conservation law. So I just make a comment on this. So if this integral is m at t equals 0, then afterward, this identity always holds. We can also rephrase this property for U level, but maybe I skip it because of the restriction of the time. The difficulty is already I discussed, but anyway, here we expect, as we discussed, the noise in 1D case, it is C minus 1/2 minus. It's like the derivative of the Brownian motion. Then, okay, then by the Schauder estimate, we expect the solution U lives in this space. That is the C 3/2 minus. Then first derivative is C 1/2. Second derivative is C minus 1/2, but slightly but minus sign here. Then, for instance, you consider the product. Product is here. Then this first term is coming from the derivative. Therefore, it should be a C 1/2 minus. This is a C minus 1/2 minus. Therefore, this product doesn't have any meaning because we can define the product for the generalized function if the exponent alpha beta, then if the alpha plus beta is positive, then we can define the product. But here, we cannot define this term and also this term. So this is a difficult point. Okay, our result is the following. So we apply the paracontrolled calculus due to Gubinelli, Imkera, and Perkovsky to the integrated form. Then we have a local in time solvability for general form and the continuity of the solution in the initial value parameter m and also enhanced noise, which I will explain. So actually, this is the pair of the Xi and also a certain quadratic function of Xi. So this local existence holds for general setting. So G is the general. But if you take G to be phi, that is what we discussed at the beginning. And this is the equation coming from the particle system. We can actually prove the global existence and also convergence to the stationary solutions. Because this equation has several conservation law. Stationary, limits should depend on the initial value. Okay, so the related results. So generalized parabolic Anderson model, that is the equation of this form, is considered by several authors like this, even in the 2D case. But in our case, our equation is very similar to this one. However, instead of U here, we have a gradient of U. So in this sense, slightly different. And anyway, up to now, the result for the singular and also quasilinear leading term is nonlinear. So quasilinear SPD are still limited. And studying the limiting behavior as t goes to infinity is very much limited, I think. So the first result is this one. So the local solvability and continuity in the enhanced noise. So so this is the joint work with these three people. This already published. And A is satisfied. So A should be positive and bounded, uniformly positive and bounded, and above conditions. And then if initial data is taken from this alpha, should be less than three halves. That is important condition. Then and also maybe this one also. Then we consider the approximated solution because as studied by Landim and others, they considered some convoluted noise, smeared noise. So we start with this equation, but the integrated form. Then we can prove. So if the epsilon is a convolution of this spatial Gaussian white noise, then we can prove there exists some random time t positive. So this is a local result in this sense. This converges to U. And U is the solution of the stochastic PD2. This is a singular stochastic PD defined in the paracontrolled sense, in the Gubinelli and others sense. And we can show that the limit U is independent of the choice of the modifier psi. This is the first result. In a sense, G is general, not necessarily phi, not necessarily related to A. So this is that, but only we have a local result in time. So the proof of this theorem is just we follow the strategy of the value and I think Derivation and Hoffman-Over. It's a result for the generalized Anderson model. They actually linearized in a sense. So, but just putting this term and subtract from the dt this term, and also then from the right hand side you have to subtract the same one. So this is a linear operator. This is a linear operator. Of course, you have to control. This is a bad term, but based on this linear term, you can rewrite it in the mild form, and this is taken through some heat solution of the heat equation. But anyway, just rewrite in the linear equation. Then they actually reload the problem into a fixed point problem on a proper space by paracontrolled. That's and also using the decomposition. But anyway, if you do this, only term which is ill-defined is this quadratic function of Guzai. So Guzai is a space-time white noise. Then this you act first derivative, but Laplace minus Laplacian inverse. So once you integrate, but still this is the C minus half minus. So this product is not defined, even if this regularized. This is called the resonant product. But anyway, this is not defined in the usual sense. But once this term is defined, then otherwise, other terms actually we can apply the purely fully analytic method. So we call the pair of this Guzai and also this quadratic function of Guzai enhanced noise. Once these are given, then we can apply the usual in a sense. So stochastically, we have to define this term, but otherwise it's okay. So roughly a proof goes in this way, just to linearize. Then I want to go to, okay, so I have another, this corollary, because we are discussing for the actually original equation is solved for the rho is the density, therefore gradient you should be a positive or a non-negative. So in this sense, we have a comparison theorem for you, gradient u. Sorry. Okay, if Guzai is smooth, then this is standard. Then the solution is, in a sense, continuous in the enhanced noise. We can take a limit, and then we have a comparison type theorem. So we discuss that we can discuss the equation for the density, which should be positive. Now we come to the global solvability. Here we take a G equal phi, and therefore we consider this equation. This equation 4, actually, so alpha, we take slightly smaller region than before, but anyway, alpha should be less than 3/2. Then Xi should be Xi to contain the spatial white noise. Xi should stay in this space because 3/2 minus half gives you minus 1/2. Therefore, spatially Gaussian white noise lives in this space. Then okay, so then this is okay. This appears as the limit of the okay, so this has the origin in the particle system anyway. So then we can show the global solvability. So first, we want to construct the stationary solutions. A bit complicated, it seems, but anyway, first we integrate Xi, then we call it eta. And then by using eta, we define theta in this way. Maybe you don't see what, but anyway, this becomes a periodic function. The reason why we consider this theta and also the mu, this is the constant and defined from Xi. Actually, the reason why we consider these quantities, this is satisfied this ODE indeed, ODE. And therefore, multiplying any z, which is a constant, this is satisfied because you take another derivative of the constant mu, that becomes 0. Therefore, this one. This means if we define the V bar, the phi inverse, so this we consider phi of, once you define V bar in this way, this term becomes phi of V bar. That means the phi V bar is the stationary solution of this equation. This right-hand side vanishes if we construct V bar in this way. So we have, and also we can move z. Therefore, corresponding to the conservation law, we can construct several V bar. Indeed, we choose z by this identity, and then V bar m becomes the stationary solution, which corresponds to the conservation law m. And then we have this result. This is a result with Xie, and this is published stochastic PD online. If we assume V0, we take from this space, then this SPD5, this one, which has a particle origin, has a global solution anyway, always. And if this quantity is not so large, this is small, that you don't see, but anyway. For example, eta is periodic, then that means that if eta 1 is 0, then this is 0. Therefore, if eta is periodic, that means Xi is the derivative of the, say, periodic Brownian motion, then this condition is satisfied. Then we can prove the solution converges to this stationary solution if initial value has this conservation law m, then we can prove Pt converges exponentially fast to this stationary solution V bar m. In this sense, in the norm is taken from this the solution space, and I write only the V variables, but we have a corresponding result for U also integrated SPD2. Okay, then how to prove? Okay, so we want to apply the method of the energy inequality and Poincare inequality as usual, but everything is not so nice. So first for the smooth noise, and then smooth initial values. Then we extend it by the continuity in enhanced noise and the initial values, noting the main point is that this initial layer property. So if we define ftx by the ratio of the phi of v divided by theta x, v lives in this space C alpha minus 1. And the theta also lives in this space. Therefore, both Vt and theta lives in this space. And that is actually the winner space. So alpha is less than 3 halves. So maybe I should write alpha should be less than 3 halves. So we take from this space. Therefore, this is the C half minus. So this belongs to the Wiener space in a sense. Nevertheless, if you consider the ratio of these two functions, then we can show that Ft actually stays in the sovereign space H1T. That is a Cameron-Martin space in the probability terminology. So this never happens usually. If you have a two bad function, the ratio lives in the good space, that never happens. But even if zero doesn't belong to this space, for all T positive, we can prove this property. Then we can define the energy for F. Okay, okay, maybe I go to the next slide. So we can actually for the F taken from H1, we can define the energy as usual, but we put the density theta. So, but in this form with the Dirichlet form, something like Dirichlet form. Then, if F belongs to this space, we can. So this makes sense, and also we have a Poincare inequality. Combining these, we can prove this energy actually decays exponentially fast. But we need this condition. If this is small enough, then this decays. So, but if F0 is outside this space, then this doesn't hold. However, as I mentioned, we have a very nice initial layer property. So maybe finally I explain how we can prove the initial layer property. So we consider a very special form of the stochastic PDE5 that can be rewritten by using F in this form. But of course, you have to compute a little bit. Then we can rewrite the equation in this form. Then you integrate both sides. Then you get this and divide by theta, and you pick up this term, but integrate it. Then this belongs bad space C alpha minus 1. But this proves we have a gradient here. So this proves this time integral belongs to the beta space. And this shows by the mean value theorem and the continuity of F in bad space. For some tau, this should be equal. This should be equal. Therefore, at some point, this belongs to the beta space. So and then once you have this one, then you have this H1T. But T can be arbitrarily small, therefore tau can be arbitrarily small. This proves the initial layer property. Okay, maybe my time is up. So thank you very much for your attention. The future problem is to derive directly from the IID random environment, the singular quadrilinear SPD. But yeah, this is the future problem. Thank you very much for your attention.
Questions?
In your first theorem, you had a limit result up to a random time capital T.
Oh, yes.
But is it a technical limitation, or do you really expect something different at a larger time?
Yeah, I don't know. We don't very carefully think about this one, but I don't know. But probably this is essential because only when G equals 5, that is A prime. In that case, is very special. But this is unavoidable once you reduce this to the fixed point theorem. So only I can answer you is when G is equal to G equal to phi and A is phi prime, then we have a nice result. Otherwise,
Okay.
I don't know.
Okay, thanks.
Thanks.
Any other questions? Okay, if not, next time.
I have a question. Maybe.
There's a question online. So.
I was wondering. So you use the method of paracontrolled solutions to solve this equation, and I was wondering whether you could use also the method of D'Aprato-Debush in this particular case, because usually when you only need to enhance your noise with one element, the D'Aprato-Debush method could be applied too.
I don't know. So anyway, we have to define this term. This is a ill-posed term. It's a square of the xi. This should be defined. I don't know. Anyway, we use this paracontrolled method.
Okay.
Once this is defined, then everything works smoothly.
Okay. Thank you.
Okay, let's thank Tadahisa again.